A while back, I was on a conference call with a high school robotics team, and one of them asked me a question that I haven't been able to get out of my head.
I guess my last question would be like what's one piece of advice you would have for, like the next generation of engineers or people entering the workforce or college?
Okay, pause here for a second. I'm gonna let you hear how I responded to that question, but first I want to tell you the question I've been obsessing over. What kind of advice would I have wanted when I first started engineering? That led to me making a list. So today I'm going to share with you several of the things that I wrote down. I feel confident saying that if you're new to engineering or you are a maker who wants to take your designs to the next level, you'll find this information helpful. Let's jump right in. By far, the most important first step when engineering a solution is to define the problem well. Defining the problem can be tricky, especially since the problem often also has a solution already baked into it. Let me give you an example. Coworkers, salesmen, your boss, whoever comes to you and they say, we need to engineer a more efficient lawnmower. I'm going to ask you the same question without the solution baked in. We need to shorten so many acres of grass in so many minutes. One of these scenarios gives you a very narrow window of things that you're trying to accomplish. The other one gives you way more options in terms of how you might go about shortening the grass. Whenever someone brings a problem to me like this, that is a problem where the solution is sort of semi-baked in, I ask very gentle but probing questions to try to figure out if those constraints really exist. If you can master this skill, both the people skills as well as the probing questions, it'll keep you from rehashing ideas that have already been worked and allow you to really innovate. Now, if we revisit that question I asked you a minute ago, that question also has a little bit of a solution baked into it. Perhaps we could treat the grass with something that keeps it from growing so tall. Or what if we ripped out the grass and put turf down? There are actually many options available depending upon what your true constraints are. That leads me to the second part, and that is defining your constraints well. Constraints usually fall into one of three categories. That is time constraints, how quickly this needs to happen, quality constraints in terms of material and appearance, and finally cost constraints. What is your budget? But your constraints don't always fall neatly into those categories. It could be things like you have weight or size constraints. It needs to fit into luggage or whatever. Once you've got those two things under your belt, there's one more thing you need to do before you start designing or modeling anything, and that is you have to do your research. There aren't nearly as many new problems as you might think, and there's a very high probability that the problem you're trying to solve now has been solved by someone else already. Now, this can be tricky because the solutions that you're looking for can actually be in fields completely unrelated to yours. The thing that you're trying to create may exist, but has a name that you don't know of. Let me give you a quick example. You're a mechanic who has decided that there's a particular component in a car that needs to be removed, and it takes a ridiculous number of hours to get this thing out, and you want to make a tool that makes it easier to reach down into this car and get out this difficult to reach component. I'm making this up as I go here, but surgeons have to reach into very tight spaces with specialized tools to remove broken components without damaging the surrounding components. Perhaps there's a surgical tool that looks very similar to what you're trying to do, and it may inspire ideas for you. Or it may even lead to you licensing their product for a special application. Or it may lead to you redesigning their product to be a better fit for what you do, because yours doesn't need to be sterile. Yours doesn't need to be as precisely made. This gives you an opportunity to learn from someone else's design and apply those principles to your specific engineering problem. There's also the scenario where you might be intentionally competing with a product that already exists. Perhaps your goals are to make the quality better or to make the product cheaper. In either case, you still have to do your homework because you really need to understand the customers who are buying that product now and how you're going to better meet that new market. Once I've defined my problem, I know what my constraints are, and I've done my research, I'm ready to start turning my idea into a physical shape. At this point, you might be tempted to open your CAD software like I've done here and just start creating a 3D model. But this to me is the hardest part, trying to create shapes from scratch in 3D. So what I typically do is start with a 2D model first. I'll either grab my iPad like I'm going to show you here in a moment, or I might grab a graphing notebook and just start scribbling out shapes. So let me give you a quick example of kind of how I do it. We needed to be able to tilt a parabolic mirror very precisely, and this mirror is pretty heavy and thick. So what I did was I simply started by drawing out a circular shape and just started thinking about different ways that I could hold on to it with tabs on the end, how I might clip onto it from the back, but I'm not erasing as I go. I simply sketch out something and then move over to some new space, and I just let it flow as quickly as I can. Here you can see the design is getting more advanced. I'm thinking about how I'm going to clamp the mirror, how I'm going to tilt the mirror up and down, and finally I need to be able to adjust this thing up and down. So I start showing some sort of square tube column. I'm thinking about how I bolt things in place here, and then a little bit more advanced layout with bolts and fasteners with some of the tilting mechanisms being here and a sliding column going up and down. This doesn't fully define the final shape. This was just my initial idea. I took this and then I opened up my CAD package, and now I've got something to work with. Now you could do similar principles by simply doing 2D sketches, but for me, again, it was just much faster to scribble. And as you can see, my art skills are not that great. The only person who needs to be able to interpret my drawings is me at this point, right? I just need to sketch out something that'll help me get a concept down that's worth 3D modeling. You want to keep your model simple and easy to change. By the time all the people involved have had a chance to review it, even if you're just designing something for yourself, there's going to be something you want to change. Whenever you change one of those foundational elements, it's going to have trickle-down effects that'll break relationships in your model. You'll be reconnecting components, redoing mates, fixing broken sketches. A lot of that additional rework can be avoided if you carefully select what parts are mated to the origin and how things are built from there. Talking about keeping things simple, don't waste time modeling threads and other fancy things that are just for appearance. Your job as a mechanical engineer is to make a structurally sound 3D model. Now, I know what some of you are thinking, like, oh, Jeremy, you can just go to McMaster-Carr and download, this perfect bolt with all the threads and everything. Listen to me very carefully. Stop that. If you find your model being sluggish when you try to orbit your 3D model, it's a good chance because you have a ridiculous number of threads and faces that you don't need in order to conceptualize your design. Now, of course, this doesn't mean you shouldn't download 3D models, but you should definitely take the time to simplify them before you put them in your assembly. Let me give you an example. Here's my robot arm that I've been working on here for the last few months, and there's a fastener. Pretty sure I downloaded this from a McMaster-Carr. What I typically do is I'll rename it first. I will suppress the features I don't want, like these threads. Let me just turn this back on so you can see what it looked like before. What I'll normally do is suppress that guy. I'll suppress whatever is creating that feature. And bam, a few seconds later, I've got a model that is much, much faster to manipulate, especially when you have hundreds of these in your assembly. The beauty of doing it this way is if I ever want to show these features, to show it to a customer, then I can unsuppress these features and they're wrapped back in. When they're suppressed, SOLIDWORKS just ignores them as if they don't exist. That makes it much easier for SOLIDWORKS to generate this model and also to spin it around in all of its various orientations. If I have a situation where I need to see how much thread engagement I have, I simply add a split line and then change the color of the face below. From a graphic standpoint, this is a million times better than adding threads. Similarly, in SOLIDWORKS, there's some additional features like up here, you have real view graphics. Oh man, there's another one in here. Ambient occlusion is one of the worst ones. No doubt that turning these features on makes the model more attractive, but it's going to slow down your workflow. You want to turn off those fancy features that don't help you model faster. They only make the model look better. It's worth pointing out that the performance capabilities of your machine also matters, but regardless of how powerful your machine is, making these changes will improve performance. There are 3 questions that I'm usually asking myself all throughout the design process. Can this thing be manufactured? Can it be repaired? Will it fail safe? So let's start with the first one. I usually like to design with Symmetry when possible because it makes it so much easier for the assembler, fabricator, or whoever to absorb the information off of the page. There's a bonus with Symmetry as well in that when you're 3D modeling, you only have to model half of it, and then you can just mirror things over to the other side. But be careful with this. If you change something that makes one side slightly different from the other, you are greatly increasing your risk of something being assembled incorrectly, because now it looks like it should work on both sides, and it doesn't. Keep in mind, you've taken this project from its birth all the way to the 2D drawing. So you've got a whole bunch of additional information in the back of your head that your brain can sort of superimpose on that drawing. But this assembler, no matter how professional and skilled he is, only has the information on the page. He has never seen your product before. So it's very easy for you to look at the drawing and think, yeah, that's good enough for him to make it. but it's not good enough for him to make it. So make sure that your drawings are detailed and that they give the information that's relevant for someone who has never seen your product. If your item is not symmetrical, it's also helpful to consider if it might be assembled upside down or backwards. All of these things are possible even with the most skilled assembler. It's easy to forget, but you can add features that are only there to assist in assembly. For example, you might add a locating hole for a dowel pin, or you might add a little boss that keeps this thing from being put together if it's reversed or upside down. You'll be surprised how much difference that can make in speeding up assembly and reducing errors. Here's an example of a part where I have features that are just for manufacturing. As you can see, I've got two flats here. Those flats serve no purpose but to hold this item in a vise while I machine the components on the bottom. Those features don't interfere with the future use of this product, and it makes it way easier to hold on to this inside of my mill. Now, when I first started engineering, I had zero machining experience. In fact, I didn't even know what an end mill was, let alone was I gonna know to put flats on a part in certain places. I had no clue. But what I did know is that I could talk to a machinist who did know how my part was gonna be made. And that's exactly what I did. And I'd say, hey, how would you make this part? And do you have any input that might make this part easier to fabricate? And they were more than happy to give me advice. Taking a few minutes to talk to these guys will make your job easier, it'll make their job easier, and it'll make your parts cheaper. Okay, I just looked at my notes and there's a whole bunch of stuff under the assembly section. You know, managing your tolerances, using the machinist handbook and stuff like that. But as I'm sitting here thinking about it, there are a lot of engineers who follow this channel. I think it would be amazing if a whole bunch of engineers just scroll down and poured out wisdom in the comment section. Not only would I love to read those comments, but you'd be helping a ton of young engineers who follow this channel and serious makers who want to design and build better parts. So if you would, please do that for me before you click away from this video. Okay, let's move on to repairs and maintenance before I start drowning in this section here. When it comes to repairs, the first question is, does it need to be repaired? Some items are certainly so intricate, so small, they're not really designed to be repaired by the end user, and that's fine. But if it is meant to be repaired, what I usually do is I'll make a priority list. Maybe I have gaskets that need to be replaced at certain intervals, bearings that require grease maintenance. Make sure that those components are easy to access, that you've got room for tools to get in, all of that good stuff. And finally, we got to answer the question, does it fail safe? For me, this is simply looking through my design and saying, if something is going to fail, what will it be? Once you've targeted that item, you need to think about, does it fail safe? In terms of electrical components, it's where you add fuses, right? Because the fuse will fail to protect your more sensitive equipment. When designing components that need to be people safe, like a walkover bridge, then you want to steer away from your weakest component being something that fails under buckling, for example, because it's sudden and people will get injured. But if you have a component that will yield and perhaps produce cracks or other indicators that this thing is starting to fail, you've got time to close down the bridge and make it safe again. It's also important that you think about how your product is going to be used and how it can be misused, because I promise you, it will be used in ways you don't expect. One of my favorite engineering quotes is, an engineer who thinks his product is foolproof has underestimated the ingenuity of fools. I'll never forget my first interaction of trying to mitigate someone misusing my product. I worked at a firm that designed industrial equipment, and it was my job to make this laptop stand which would retract and allow you to access equipment behind it. I designed the laptop stand and showed it to my chief engineer. In all his years of wisdom, he looked at it and he said, "You see all that equipment up there? Some maintenance worker is going to use your laptop stand as a step stool to access that stuff up there." So we talked about it for a while, and he suggested that I make it look so flimsy that nobody would dare want to stand on it. And I took his challenge. I put a lot more holes in it. I used a thinner gauge of sheet metal. When I was done with it, it could definitely hold a laptop, but not much more than that. I have no idea if anybody ever tried to stand on this thing or not, but my chief engineer approved it, so I guess it worked out in that sense. Take a moment to think about how your product can be abused, but it is completely impossible for you to conceive of all the ways your part could be misused. So don't stress on it too much. The next thing I want to talk about is controlling costs. In my opinion, this is the scariest part of engineering, because as the engineer, you control most of the costs. You decide what materials are going to be used, what processes are going to be used, and if you over-design, your product is going to be stupid expensive. Engineers who are stupid expensive don't keep a job very long. Design your part too weak, and people get injured. This is not what you want either. The best engineers work very hard to find a balance between the two. It's hard, but that's your job. Just about all the decisions you make affect the cost, so let's just focus on processes for a moment. You have a product you're designing that has to be welded. The easiest option for you as an engineer is to call out fully welded everywhere, but that's going to require the most amount of time from the welder and give you the greatest risk of some rework being done somewhere on your structure. The alternative would be to have it stitch welded. Going with the stitch weld is going to greatly reduce your costs, but it's going to require you to answer the harder question of how small is enough. The same thing is true for machining. If you call out a hole with a tolerance loose enough that it can be drilled on a drill press, then any guy in the shop can do that as long as that hole is good enough. But if you call out a hole with a very tight tolerance, that shop is going to have to put that part in the hands of a machinist. That machinist is going to have to do the cam work, he's going to have to probe the part, and then machine out this hole carefully. Is that one just as good as that one?
I think that one's better.
That one's better? Okay. And at that very moment, I knew she was going to be an engineer. Another thing that significantly reduces costs is using purchase parts instead of custom parts. This is especially true for precision parts. Bearings are really precisely made, but because they're mass produced, you can buy them cheaply. And again, you should have a very good reason for making a custom bearing as opposed to using a purchase bearing when possible. This whole next section on my list is about how to innovate. Basically ways of thinking outside of solutions you've already seen before. Let's just take power sources, for example. Our minds tend to drift towards the most familiar power sources, like plugging things in. And then next, of course, would be battery powered. But there are many more options outside of that, right? There's pneumatics. You also have other options for electricity, like mechanically generating power. There's also hydraulics. Of course, each of these methods has their pros and cons. Hydraulics packs a lot of power in a very small package, but it's usually pretty slow. Pneumatics can be extremely fast, but it requires vast amounts of air storage and other auxiliary equipment. As the engineer, you can list out your pros and cons, compare those to your constraints, which you've already defined. Looking at these together will let you know what your real options are. Of course, I'm leaving out some power options here, but I expect to see many of those in the comment section. The same way that you have a lot of power options, you also have a lot of options for joining things together. When I was working in the industrial environment, I primarily thought in terms of welding and bolting. When dealing with plastics, we often see parts that snap together. That's not impossible with metals. There are also many different adhesives you can use for all different materials, including metals. The same way I suggested you talk to a machinist or a welder when looking at fabricating your parts, you can do the same when it comes to new types of joinery. In my case, I recently needed help with adhesives. I was on a conference call with an engineer from LOCTITE. I had these two plastic pieces that I wanted to glue together, but the joint didn't seem to hold up very well under load. He told me that basically different kinds of plastics require different sorts of adhesives. He sent me a 100-page user guide which showed every kind of plastic you can think of paired up with all these different adhesives. And most important to me as an engineer, you can see what kind of shear and tensile strength you can expect from the various adhesives. What engineer doesn't love that? During that same conversation, we started talking about their 8000 series adhesive, which is designed to be a weld replacement. Another option I wasn't aware of. This really piqued my interest because it addresses two issues I'm dealing with on a project right now. The first issue is I have two parts that'll be pre-machined that I might have to weld together. This is a practice to be avoided because the welding can distort your machined fascias. I also want to attach a small piece of machined aluminum to this fixture, but I don't want to use bolting in this application. And there's one more benefit I want to point out before I leave this topic. Just about any guy in the shop can be proficient at using this in a single afternoon. But if you want somebody to lay down nice looking welds with minimal distortion, you better believe it's going to take a lot more time and somebody with way more skill. Frankly, I was super impressed that I could get an engineer on the phone who could answer my technical questions and help me solve this design problem I was having. When I got off of that phone call, I knew I wanted LOCTITE to be a sponsor on this YouTube channel. And apparently they agreed because they're sponsoring this video today. I want to say thank you to LOCTITE for sponsoring educational content like this on YouTube. That's what allows me to build better projects and share my passion for engineering with the world. My goal here is not to sell you a package of adhesive. My goal is to give you the tools that would allow you to build better, more cost-effective projects. I only recently became aware that adhesives was a tool I was underutilizing because I didn't really understand what it was capable of. And by the way, if you want to do a service call with an engineer from LOCTITE the way I did, there's a link in the description. All you have to do is fill out that form and someone will reach out to you. If you're looking to boost your knowledge of adhesives in general, LOCTITE has a free educational platform called Xplore, and it's pretty neat. There are only 2 courses there now, but LOCTITE has assured me that there are many more to come. I say that's pretty good. Here I've got a list of what I'm calling technical gotchas. I don't think I'm gonna get into all of these, but I'll just mention a couple just so that you're thinking about these things that could possibly happen. For example, when you bolt 2 different materials together, they expand and contract at different rates. So if you're gonna put this out in a very cold environment or a very hot environment, that may affect your bolting or put stresses on your welding. You just wanna be aware that these are things that can lead to problems. Of course, this is just one more thing on the huge list of things you have to think about when designing a product, but that's the job, right? It's your job to solve the problem. I've tried to pack this information as densely as I can, but that means you're probably not going to get it all on the first try. So it might help to watch this video more than once. And also, there's going to be a lot more stuff down in the comment section. In fact, I would say if you do any kind of work related to design or manufacturing, we'd love to hear from you. Even building this robot that you saw behind me earlier, it wasn't just mechanical design. There was machining, welding, I was doing electrical design, I was doing programming. There are a lot of different skills that mechanical engineers have to touch, and it will be good if we learned a little bit from the experts. I'm really excited about reading the comment section in this video. We just might create the best resource for engineering advice on the internet. As promised, I'm gonna show you the rest of that clip, but I should probably tell you who these guys are. So this is team 516 Gears on Fire. This is a high school level FIRST robotics team, and they built this amazing, completely autonomous robot. Their robot is about to compete at the national level, and I wanted to talk to them about their design. Anyway, you can find out more information about them at the link in the description. I'm just gonna hit play right now.
What's one piece of advice you would have for, like the next generation of engineers or people entering the workforce or college?
I would say by far the most important thing is that you realize your job is to solve problems. So when somebody brings you a hard problem, that's sort of the point, right? That's why you're there. And if your attitude is always, well, I don't know yet, but I'll figure it out, that's the guy I want to hire. So yeah, I would say if you can master that, if you can always have the attitude of, like, I don't know yet, because you're going to get lots of problems that you don't know the answer to. You want to be the guy who has solutions and not problems.
Thank you.